Hello to all of you. Thank you for joining this short video. I was asked by my friends organizing my seminars to make a video, but I thought I would make it a little bit differently rather than just announcing a date and showing the title and making a few pretty basic comments. I want to take a few minutes to convince you that if you attend this bims2 seminar, you will most probably learn something useful for your daily job. So the bims2 seminar is about understanding plastic part failure, essentially. We call it understanding mechanical properties of thermoplastics. The focus is really on understanding part failure. And it tries to cover most of it in terms of short-term versus long-term performance, but also different materials, amorphous, crystalline, with or without fibers. Now, if you think about it, what we really hate is when our parts fail in an unexpected way. Now, you might object that, well, failure is always unexpected. Who would ever design a part for failure? Well, sometimes we have to do, like for airbags to deploy, but most of the time we design for the part, to survive the load and the environment for the prescribed expected lifetime in our application. So you might say, failure is always unexpected. Well, think about it. What about overloading? Well, if we badly overload a part, like we apply a stress, a force that is ridiculously high, of course the plastic part will bend and deform or possibly break into pieces. And that is definitely not an unexpected finding, right? We all expect parts to fail when they are overloaded. So there, our job is to specify correctly, the load range that the part will sustain, and that includes, the right material selection, good processing, good part design. So then again, overloading is not unexpected. And if you really think about it, most ductile failure typically relate to overloading because ductility is typical of, fairly short-term sort of loading, not super fast, it's not impact, not super slow, it's not creep, but in the medium range, which is typical of, our observation time, which is seconds, we're probing parts at a strain rate where we hope and we try to select materials that behave in a ductile way, meaning they will fail by yielding. And this is why yielding is mostly associated with expected failure, overloading, right? So brittle failure is really what we don't like, what happens mostly when we least expect it to happen. And so I will spend a lot of time during this seminar really trying to explain, the completely different physics of ductile versus brittle failure. Now, a lot of people are aware of that and they will say, I know, ductile failure is when the part deforms in an irrecoverable way, so it's done. The part failed because I reached yielding, plastic deformation. I cannot, the shape of my part is compromised, so the function is compromised, or even just the look of the part is compromised. That is an heritage of metal. I mean, metals, surprisingly, are much more plastic than polymers. Now that sounds like an oxymoron, right? It's kind of crazy, but that's what it is. You know, with no exceptions, metals go into plasticity at a fraction of a percent. People have developed very special alloys to try to reach maybe 1%. But so metals go into plasticity very quickly. So we design parts to stay away from the yielding of metals. And we associate yielding with, you know, the limit, the load limit of our metal-based parts. Now, plastics are different. They yield at 5, 6, sometimes 7 strain, which is a lot. And, you know, there's not so many applications where a strain of 5% is actually acceptable, you know, just from a geometrical point of view, from the functioning standpoint of your application. So in a sense, that's why we tend to consider that yielding in polymer is what you see if you badly overload the part and strain it to 5-6%, which we are not supposed to do most of the time. Okay, so which failures do we consider unexpected? Well, basically all the brittle failures. And you know the distinction, brittle is when your part breaks into 2 pieces that you can pretty much put together again, possibly glue, and with no visible plastic flaw or, you know, irrecoverable deformation of the part. So brittle failure is typically what we're afraid of for good reasons, because it seems to appear when we don't expect it. Now you might say, but, you know, in my company we have 5 people running finite element. You know, they're experts. They run ANSYS, Abacus, stuff like that. Okay, so how do they help you designing your parts? Well, there are different philosophies. But if you just look around, ask inside your company if you do run finite element, or just check, Google around, you will see that, I don't know, 50, 60, 70% of people running finite element to help you design your plastic part will strongly focus on von Mises stresses. And they will compare that to your tensile yield stress value from the data sheet. So they essentially tell you, well, we look at this equivalent stress, as we call it, von Mises. If you hit a high number above the yield stress, there you go, the part will fail. And that's correct, that's fine. But it is a choice. From the very beginning, if you only look at von Mises, you're only looking at yielding. And that's something that not everybody gets quite correctly. So von Mises only contains shear components. Shear components of your load can only promote failure in a ductile way. So if you look at von Mises and as a failure criterion you use a yield stress of your material, you will never, ever, ever be able to predict brittle failure, okay? So, well, so maybe half of us are already missing the point there, because, you know, we get part failure, the one that we least expect are brittle. Well, you cannot predict those by using, you know, a ductile criterion like yield stress associated to an equivalent von Mises stress. But the smartest FEA people amongst us will say, well, no, I don't do that. I'm using principal stress, maximum principal stress. So if you Google around, and I'll show that in the seminar, a lot of us, you know, digged a little bit more into it, and they figured out that, well, maybe I should use the maximum principal stress. And if you don't know what it is, I will explain that in details, but essentially you can describe any load in 3D with essentially 3 numbers locally at least, and these are called principal stresses. They're ranked from the highest tension to the lowest, possibly in compression. So sigma 1, the biggest one, positive, is the highest level of tension. And then you can use that and again put some failure level threshold against it, which most of the time is still the same, like the yield stress, which is already debatable, because suddenly you're not looking at the average shear level like von Mises, but you're still using a yielding threshold. So it's a kind of a mismatch. You are using maximum tensile stress because you figured out that, there's more to failure than just yielding, but you're still using your yield stress as the maximum sustainable stress, which is not quite sufficient. And then I will show you that failure, and especially brittle failure, which is associated with, of course, crack opening, which we can also describe as cavitation, is really linked to the overall tensile state in your part. And there's 3 stress components. You have to look at the 3 stress components and combine them as appropriate to really describe the level of tension. So if you don't that, and I will show you that, with a principal maximum stress, you will also miss most of the interesting failure conditions. So this is all about what we call triaxiality, the sort of 3-dimensional level of tension. And it turns out that that's how polymers fail in a brittle mode. That's when the global 3-dimensional tension is so high that you start cavitating and creating a crack. Okay, so we'll look at that into details, and I'm sure even the most seasoned of you professionals working in plastic part design will find it interesting, and learn something. Well, I guess this video ended up being already longer than I anticipated. I don't want to take more of your time. This was just a little bit of chat about one very tiny slice of my seminar, bims2. So if you're interested, the upcoming session in Copenhagen is April 9th and 10th, as you can read here, very close to the airport in Copenhagen. Subscriptions, registrations to be made with ATV SimUp. Just Google, you'll find the online tool to register. We already have 5-6 people. We have sessions coming up in Germany, public sessions in May and later in November. And, I'm sure we'll come up with some private sessions if any companies show up, as they typically do during the year. Thank you for listening to me, and hope to see you. I'll post a similar video about bims1 for those who are not that interested in mechanicals, but mostly want to focus on the injection molding process itself. Bye.